when he explains things, you actually understand it, which is quite a different skill to have, and that means that you really understand what you're doing. So I want you to share his ability with you today. And I hope this will help you to get more understanding of what this deep learning thing seems to be playing. So.
Yeah. Thank you, David. Well, thank you for having me here. It's a pleasure to be here in La Coruña. So yeah, I'm going to talk a bit about deep learning. David said the title of the talk, Demystifying deep learning. I'm not sure about what is meant by that, but I'll try and do my best. So this is basically what I'm going to cover today. First, I will introduce a bit like deep learning, what is all this about. I will talk about feed-forward and recurrent neural nets. And that is the first part of the talk. The second part of the talk is I will focus on application of deep learning into vision, which is what I'm working on in Oxford. And then so I will present 2 projects that we are doing there. Okay, so what is deep learning in general? So the key point, also as John was saying, is is about learning abstractions from data by using a structure of layers, usually a stack, and usually also many of these layers. We have a big stack of them. Now here I'm going to focus on supervised learning, in the supervised learning case, along the talk. So basically we have a set of instances, for example, I will put in as X, which in this case the image that we have in here. Now at training time we have a label attached to each of the instances, Y, which in this case is orange. And then in supervised learning what we want to do is to learn a function that maps from X to Y. Now in deep learning this function is just, as I said before, this stack of layers. These layers are defined by a set of parameters. All of them are denoted by W here. And then the purpose is just to learn this W so that we can make the mapping. Now, one important thing here is that, we have several layers and some of them are non-linear. So they represent non-linear activations. And that is very important because that allows the model to learn more complex functions, functions that are more complex than linear functions. And that's like basically the main thing of this. Now, how does it work? So at inference time, we have an input image or an input instance in the general case, and we process it through the layers until we get an answer at the end, in the top. Now, this answer may be correct, may be wrong. At training time, we know if it is wrong. So now, if we want it to learn from its mistakes, then what it is done is to do backpropagation of the error through the network, so that the gradients of the we get an error, so the gradients of this error are computed through the layers. So one way of looking at this is that basically an error is made, and then in the backpropagation we look for how much responsible each of the weights with respect to this error that is being made. Now, once the gradients of the error are computed through the network, then we move the parameters, this W, towards this direction so that we minimize the error that is being made. And it is called gradient descent. Now, one very interesting property of this is that at the end, backpropagation is basically the chain rule in derivation, in computing gradients. So that implies that basically in terms of implementation, we can implement forward and backward propagation for each layer independently, and we can just plug layers together. That is that we don't need to, when we implement a network, we don't need to start from scratch, but instead we can just plug layers that we have already implemented. That is quite interesting because, for practitioners, it's very easy to start tinkering with networks, just plugging layers together. Let's see if this model works, putting this network with this data, and let's see what we get, and things like this. So actually, if I know how to do this, I'm going to show you an example of that. Here. Yeah, so there are many frameworks for to play with actually to do deep learning. There is, for example, Caffe in C++, Theano in Python, MathConfNet in MATLAB. Here I'm going to use Torch, which is quite an easy framework to use. This is a very simple example. In the first box here, I'm going to run now. This loads some libraries for neural nets and image processing, and then we load an image. Oops. Now, here, what I'm going to do is I'm going to create one layer, which is a spatial convolution. So basically, we learn a set of filters that will process the input, and then we will get the result. So, by the way, here, here, we define the parameters of the layer, like the properties of the layer. Basically, the input, this number is the input of number of channels, which in this case is 3, because the input image has 3 channels, RGB. The output is 4 channels in this case, and then we learn a set of filters that is 7 times 7 pixels. Now, if we run this, the weights, the initial weights are initialized at random. So we get a set of outputs from this. Given that the weights are initialized at random, if we run this another time, we get different sort of results. Some of them may be useful because they may detect filters, some of them are not, but we are not learning the weights. So the point is actually learning them. We can create more complex networks. Like before, it was just one layer, but we can create networks as complex as we want. For example, we can use this sequential structure in which we keep adding layers. As I said before, introducing nonlinearities into the network is important, and that's why we have this ReLU here, which is a nonlinear activation. And then if we run this, we get same sort of thing, but slightly more complex, usually. So, yeah, again, weights are initialized at random. Now, I need to show, if possible, results using a network that has been already trained. Let's see. Might take a bit of time, because it's running CPU instead of GPU, but in any case, the point here is that in order to, we are seeing the method of learning, performing inference by calling at the forward of each layer, but we can do training, we can compute the gradients by just calling the backward pass of the layer. Well, apparently, I think it's frozen. I can come back to that later. Okay, let's go back. Where's the pointer here? Oh, perfect. I think it's frozen. Anyway, so back to here. So yeah, basically, it's pretty easy to start tinkering with this and to start doing stuff. Now, so far what I have said is there is nothing really new. So one question that you may be asking is what has changed from the 90s? And the truth is that essentially or conceptually there are not many changes actually. So the main thing is now we are able to create networks and to actually successfully exploit networks that are very, very deep. And actually, we can see here is a very, very deep network. Each of the lines here is a layer, and in total it has 152 layers in this one. This one was the one that won last year's ImageNet challenge. And the key thing here is that, well, now we have big amounts of data for some problems. And that is really important because if we don't have big amounts of data, then this model will definitely overfit because there are so many parameters to learn. Actually, as John was saying before, if we don't have big data, maybe this is not like the best sort of approach to employ. Maybe we should go to other sort of methods. But if we have big data, then this, in some cases, is very a good approach to take. And the reason is that usually, traditionally, in machine learning, supervised learning, one of the big concerns is that the model may overfit the data, the training data, so that it is not able to generalize to the test or to new data. But now, in some cases, when we have such a big amount of data, well, overfitting is no longer a problem. Actually, the problem that we have sometimes is that the model is not able to exploit fully the data. Is in a way is underfitting. So that's why, oops. Okay, that's why having the capability of building very deep networks and actually learn them is very useful. Now, another very key point is that we now have much faster hardware. We have GPUs, which are able to exploit parallel sort of computations like convolutions and so on. And then finally, also like new sort of tricks, like methodological improvements. I would point out the one here that the nonlinear activation, as I was saying before, nonlinear functions are essential here. And the thing is, in the 90s, the activation functions that they were using were mostly sigmoid or hyperbolic tangent. But now it's much more common to find this ReLU function here. And that has nicer properties because the ReLU avoids problems like the vanishing gradient problem and so on. Okay, so far I've been talking quite generally, but assuming that the network is feed-forward. That means that basically you have an input, you put it through your network, that is a set of layers, but you can see this as a black box, and then you get an output. And that's great. I mean, we have seen that it performs really well in some problems, like for example, object recognition and so on. It has improved the state of the art by far with respect to previous methods. But still, it cannot compare, or you can employ these sort of networks with other tasks that are more complex, but still we as human beings can easily do. For example, reasoning, translating, object counting, and so on. And the point is, well, at the end, our brain is much more complex than just a feed-forward network. So in order to try to bridge the gap a bit, so what the next step, in some sense, is to work on recurrent neural nets. So they, in a way, are quite similar. They receive an input, they produce an output, but they also have like backward connections, like the one that we see here. And these backward connections allow the network to learn by itself what it needs to remember from the data that it has been seen so far, in order to minimize the error. So they are really versatile. They can be applied in a myriad of problems. I'm going to review here a few of them. So these are like some set of cases where I'm going to go one by one. So the first one is when you have one input, you produce one output. This is quite similar to feed-forward nets. The difference here is that the network is able to keep refining the output that is being produced. And one example of this is semantic segmentation. I will talk a bit more about that later. Another case is one-to-many, so the input is one thing only, and then the output is a sequence of elements. One clear example of this is image caption generation. So the input is one image, and then the output is a set of words that describe the input image. And you probably have seen this before. It works decently well. Now, another case is the opposite, many to one. In this case, well, one example of this would be text categorization. Basically, here we have a set of news, for example, and then we want to classify them among a set of classes. So the input will be the words defining the news, and the output will be the class. Now, many to many in this particular configuration. So in this case, the prototypical example is machine translation. Basically, here we have like sort of two RNNs. The first one is an encoder, which is the first three elements that we see here. They receive an input, which is a sequence of words. The network keeps in its state, in the memory, the meaning of what it's been reading so far. And then once it achieves the end of the sentence, then the second part, which is a decoder, takes action and then produces the same sentence translated into a different language. Now, finally, we have another many-to-many configuration or many-to-many case, which is, basically at each time we receive an input and we want to predict an output. And basically, this is very useful for time series prediction. Okay, so that covers the first part of what I'm presenting today. This second part is, as I said, is basically some projects that we've been doing in our lab. These are the people working on there, segmented. And basically, actually, I'm going to talk about two projects. The first one is about semantic segmentation. So semantic segmentation consists basically in recognizing and delineating the objects that appear in an image. So that at the end that boils down to classify each pixel of the image to belong to different classes. For example, here you see a motorbike and a person. Why is the semantic segmentation useful, first of all? So actually there are quite a few applications that this is very useful for. For example, one of the projects we are working on quite a lot in our lab is to help partially sighted people by, they have like a set of spatial glasses that can project information, so we provide them with important information for them to perceive. But this is also very useful for allow intelligent agents to interact with the environment. For example, navigation of cars, allowing robots to see where the objects are and to allow them to grasp them, and so on. It's also useful for editing images by, segmenting the objects, and then you just have to say, you just cut the TV or whatever. Also very useful for medical images, like for example, segmenting tumors or segmenting different brain regions in fMRI scanners, also dental cavities, and so on. So I hope that by now you think that this is an interesting problem to work in. It has some applications. So the question is, how do we deal with this? How do we solve it or face it? So we started by using a model developed by Long and other people almost 2 years ago. And the point of this model is to have a fully convolutional network. Basically, it has a lot of convolutional layers that keeps the spatial information across the representation inside, but the representation keeps decreasing because of the nature of convolutions. So at the end, they introduce one or a set of deconvolutional layers that basically transform the solution back to the same size as the input. So basically, they get semantic segmentation of the input in here. Actually, similar ideas can be found and actually can be traced back to the 90s. As I said before, there are essentially not too many new things here, like in deep learning in general. But to be honest, this is a very nice paper. They went by long. They actually improved the state of the art. They include some interesting elements. And actually, they got really good results. As I said, they significantly improved the state of the art at the time. But one aspect that we saw is that the solutions, the predictions that it gets, are quite poorly aligned. Like the definition of objects is not quite there. So, for example, these are some of the results. So you see the shape of what is being predicted, but you cannot see what is going on. So we wanted to work on this particular aspect, and what we did is to study or using conditional random fields. Conditional random fields are quite a well-studied graphical model that is being used for in cases where we can exploit contextual information. And in particular, what we want to do here is to add into the model the prior information, the prior knowledge that pixels that are close to each other and have similar color intensity are likely to belong to the same class. And that's the key thing at the end. Conditional random fields are based in the simplest form in minimizing this function here, where the first term is correspond to the unary terms. It's basically the predictions made for each pixel independently. So, for example, we can use for the first term the predictions made by the FCN that we saw before. Now, the important point here is this second element, this second term here. So, this terms, the purpose of it is to penalize similar pixels having different labels. Now, conditional random fields has been studied quite widely. A lot of papers have been proposed, and is quite well studied. So here we built on a paper developed by Graham and Colton. It's a very nice paper. They won an NIPS award that year, and basically, well, they developed a very effective and efficient way of performing inference in a densely connected conditional random field. I'm not going to go through the algorithm, but one important point here is that they start by having they start from one original solution, which is in our case it could be like the unary terms of the FCN, and then they keep refining it iteratively until they achieve there is some sort of convergence in the results. So there is no point in keeping doing the iteration. So first of all, what we did here is to express the elements of the steps of the iteration as layers in a convolutional net. These layers are quite common. They are widely used in general, except for the bilateral one over there that we need to implement. But the good point is that all layers there are fully differentiable. So we can do backpropagation, and we can learn all the parameters in the path and actually keep the gradient backpropagating through the previous part. Now, as I said before, this is an iterative process, so this is only one iteration. So we need to create this loop. And again, what we end up with is a recurrent neural net that keeps refining the input, that keeps refining the prediction until it gets an output. Again, everything here is fully differentiable, so that's nice, we can learn. Finally, we just put this module together with the FCN that we saw before, and then we can train everything end to end, so that the network can learn from the training data. Now, we have created a demo for anyone to use. This is available at crfsrnn.tor.vision. These guys here, we make this demo, so I sang Sarija Sumana myself, supervised by Filtor. And actually, we also won an award last year in ACCV for the demo. And also, if you want to play even further with this, we have the code and models available in GitHub here. So now I'm going to show a few of the examples that you can well, you can use in here in the demo. For example, we see these images of cats here. We see the result is quite well delineated. You see all cats are very well segmented and also detected. Like we have cat there. This is another example in which you see several different classes. All of them are quite well detected, even the sheep that are in the background, and also the bicycles. Now, of course, this model is not perfect. It fails sometimes. We have found mostly two sort of errors. Like one is when it fails to classify or to detect one object. For example, here it detects the cat as a bird, possibly because of the environment, which is not too common. And the other kind of mistake or the error that we see is that although it detects the class well, it is not able to delineate well the object. And that happens whenever the elements around the object are very, very similar to the object. The good thing is that usually doesn't happen in the real life. People have also submitted all sort of examples. For example, here, this strange thing between a bird and a dog, and the model is able to do quite well on that. And that's pretty much this part, this project. Now, I'm going to talk about this second project here, and in order to do that, I want to do a very short experiment. So I would like you to have a look at the following image for a very short time. Okay, so what is in here? I think it's pretty obvious that the answer is there are bottles. Yeah. So indeed, there are bottles, and this is a very easy question for us to answer. And this is a question related to object recognition. Now, the next question is, where are these bottles within the image? Well, it's easy for us to say, well, they are sort of spreading across the image, sort of in the center, but covering the whole image. And again, that's quite easy for us to see. And this question is related to semantic segmentation, which is what we saw before. Now, one last question is, how many bottles are in the image? Now, does anyone know? Fine. Good. Otherwise, I should leave. So basically, the point here is that, actually there are 2 points that I want to make. First of all, this is a difficult question for us. And the thing is, this question is also related to instance segmentation. So we want to segment all of the instances of the bottles appearing in the image so that we can count them. This question is more difficult to us mostly because when we want to count a set of elements in an image, if there are more than 4 or 5 elements, we have to go them one by one, like sequentially going this. And we have to keep in memory both the number of elements that we have segmented or counted so far, and also the parts of the image that we have covered. So this requires like this iterative process. So here in this project, we work on instance segmentation. And then what we want to do here is to, in some sense, to mimic the way we count elements. So in order to do that, we employ another kind of recurrent neural net. And basically the way it works, ideally, it should be something like this. So you get an input image. In this case, you can see a set of shapes here. Now, first of all, it has a memory inside that is initialized to be nothing. So there is nothing in memory to start with. Now, at time 1, the network is to segment one element, and then it should keep in memory what is being segmented so far, so that it doesn't count it again. Now, at time 2, it does the same, segments another instance, it keeps that in memory, and so on. Until eventually, it gets, well, there are no more objects to segment, so then the network says, okay, let's stop here. One important point to see here is that what we provide to the network at training time is just the input image and the masks here. We don't tell the network at all anything about how it should manage the internal memory. So it is the network itself, the one that should learn how to use the memory. So it should do something like what we see here. So the actual details of our implementation of this idea are the ones that we see here. So first of all, we have an image. This image is passes through this fully convolutional network that we saw before, so that we get the script, like a set of features per pixel. And now this is introduced into this conv LSTM, which is a sort of recurrent neural net that keeps a spatial state of the image, so that the network is able to keep track of what part of the image has been segmented, and so on. Now it goes through a spatial inhibition sort of module, which basically helps to segment the current element being segmented. And finally, well, it produces a mask and a score, a confidence score that says, okay, if it is above 0.5, I accept it. I consider that to be an instance. Otherwise, I say, okay, there are no more instances in this image, let's stop. Now we have a loss function that once everything is predicted, then there is an evaluation that compares that with the ground truth. And then in the case we are in the training stage, then we can backpropagate the error back to the whole pipeline. Now we have seen that we have done several experiments. It works quite well in several cases. The first experiment that we did is on leaf segmentation and counting in plants. Here in the top table here, we can see that our method perform, well, this is like a counting sort of a measure. So the smaller the better. And we can see that our method performs better than the others. And this is, I think, quite remarkable because these other methods here were explicitly designed to deal with this sort of data, with plants from above. Very particularly this. They contain a lot of heuristics in the inner state. So in some sense, we can see that the network is able to keep track of what has been segmented so far. So the leaves that has been segmented appear darker. So that's like quite nice, basically. So we have moved to like a more complex sort of settings. So like segmenting leaves is sort of simple. So we went to segment people, like different sort of subjects, which present a lot of like a much bigger challenge because people like they have a different clothes. They may appear farther in the image or closer to the camera. They have different genders and so on. So in general, we see that it performs quite decently well in comparison to previous methods developed last year. It does better. So this is our method. This is our method using a CRF to further improve the segmentations. We can see that it does better than the others. And that pretty much covers everything I want to say. In general, I think that these are exciting times within deep learning and general machine learning. We've seen that deep learning is great to, like, for example, for practitioners. The modularization of the model is very easy for anyone to start tinkering with how these things work, but also it's easy to keep going on and to practice with like more complex models. If you have data, you can really be able to learn quite complex and very nice models that are able to perform complex tasks. And also there are lots of open libraries available, so it's quite easy in actually almost any language. Now it's also very, very exciting within research. I've been talking here, I've been focused on supervised learning, but basically you can apply the same sort of ideas in, for example, unsupervised learning, reinforcement learning, and so on. And also there are a lot of open problems. And in particular, also John commented a bit on that, theory on deep learning is way, way, way behind the empirical results that we are getting. So there is a lot to understand. So we know that these networks work really well because we do experiments, but we don't know exactly why, or we don't know when this will work well, or in which settings this won't work, and so on. So thank you for your attention, and I'll be happy to answer questions.
Anyone have a question for Bernardino? So in the demos we were showing a lot of demos.
Yeah.
We were saying all this time that you need a lot of data
Yeah.
to achieve some kind of result. What is it? What is the size of the data set behind the demo in the web or the leaf counting or the semantic segmentation?
Yeah, that's okay. So, for example, for the semantic segmentation demo that we have in the web, we use the publicly available data that is composed of a set of around 80,000 images, and yeah, around this number. The thing is, for semantic segmentation, in some sense, we have as many instances as the number of images times the number of pixels within an image, because you have a decision to make for each of the pixels. So at the end, it's a huge number, like huge number of instances in some sense. For instance segmentation, for example, the plants data set, that is actually very, very small. We only had 128 images, but the thing is that the model that we want to learn, we know a priori that is to be invariant to rotation and flipping of the image. So we augmented the data set by using these transformations. And as I said before, also we have the like a decision to make for each pixel. So at the end, the model doesn't overfit. But yes, there are also these sort of tricks that are like not, like they are unpleasant, like this pre-processing, like this data augmentation. But yeah, you need to do that in order to get decent results. You would say that there's a trade-off between the amount of feedback you get from the expected output and the amount of data you need to train something to get some. Sure. Yeah, you mean, for example, if you have an image and the output is only... It's a binary pattern. Yeah. It's a binary task. Yeah. You need much more data to achieve something there, for example. I think so. I mean, definitely in the case of having several decisions to make for the same instance, yes, definitely that's the case. Actually, at the end, in this particular case, getting a fully convolutional neural net, that can be decomposed on having one net applied to small patches and getting one decision, like one classification for each of the patches. So at the end, you have a lot of decisions to make, therefore a lot of training data. Once again,